a little bit of the history of my involvement in this project. It was sort of by accident. Wayne and I both attend the Alabama Academy of Science meetings, and he was the chair of the STEM education section. So I was at the STEM education section watching the talk, and he described this new satellite project that he was working on. And, I asked some questions, and next thing you know, I'm being asked to be part of the project. It's been an adventure. The co-authors on the paper here, David King is a senior physics major here at UNA. He's interested in going into astronomy as a career. He's more of a theorist. And Harmony Waldarbor, she's a sophomore student. She presented a talk on light pollution at the Alabama Academy of Sciences meeting that was hosted by Athens State, and got asked to be part of the project by Wayne. And so that's how she's involved. Okay. Now, the interesting thing about this is that, SARA is, sort of the stepmom, so to speak, of this project. And the way professional astronomers do it is that we design the science, and then we design the project around the science. And here we've designed the project, and now we're designing the science around the project. So it's been quite an adventure to see a different way of doing things in terms of procedures. The science key to the whole thing is the frequencies that the satellite is going to be observing at. And I just found out that instead of 300 kilohertz, it's going to be 20.1 kilohertz. But I don't think that changes any of the conclusions that I'm about to draw. We're trying to hit a moving target here, and the satellite is still being worked on and designed and finalized. So in any case, the key to the whole thing, as most of you probably know, is that there are what we call atmospheric windows. Certain energies of the electromagnetic spectrum simply don't reach the ground. Some of them reach high altitude, so things like the SOFIA spacecraft working at infrared, they can operate. Some of the balloon-borne stuff with the microwave background. But there are entire branches of the electromagnetic spectrum that are of interest scientifically that simply can't be observed from the ground. Now, a lot of the radio region of the spectrum is observable from the ground, but once you get past approximately 30 meters, then the ionosphere reflects the energies back into space, so that very long wavelength radio astronomy simply can't be done from the ground. Now, this provides the scientific opportunity to do science that simply hasn't been done by anybody else before. Very limited amounts of observations have been done at very long wavelengths for this exact reason. The satellite is still being finalized, and so the last conversation I had suggested roughly 300 kilohertz. That's been again shifted to 20.1 kilohertz. And the indication was that it was going to be a helical antenna. I'm not sure what the difference between a toroidal antenna and a helical antenna is, but in any case, a helical antenna is the sort of thing that's sitting in your cell phone. They have the advantage of being sensitive to circular polarizations, which if the satellite is tumbling, apparently is going to be an issue. And they also are omnidirectional in the sense that they detect radiation from all directions. The reception of the antenna depends on several parameters. The first is the actual diameter of the loops of the antenna itself. It depends on the number of turns in the coil itself, and also the pitch angle, the angle that the sort of plane of the turns makes with the actual axis of the antenna. All of these things affect the beam of the helical antenna and the gain that you receive. There's two modes for observing with the helical antenna. The first is the axial mode. Basically, this is the direction of the axis of the antenna being pointed, and it's the mode when the diameter of the antenna coils is similar to the wavelength. Our satellite is going to be 10 centimeters by 10 centimeters by 30 centimeters, whereas the wavelengths are going to be hundreds or possibly even up to a kilometer in wavelength. So we're not going to be observing an axial mode. The diameter of the coils is going to be tiny compared to the actual wavelengths of the energy. So this means normal mode. This means the satellite is going to be sensitive to radiation that comes in roughly perpendicular to the axis of the actual antenna. This is what we have to work with, and it has the disadvantage that it has relatively low efficiency compared to axial mode, and has limited bandwidth. However, as we'll find out, the signal that we're going to be receiving is going to be strong enough that it's probably not going to be an issue. A lot of this talk now is a little bit out of date based on Wayne's presentation earlier. One of the things about actual studying astronomical sources, you need to know where you're pointed. So the signals are being received from what we call a region of the sky that's included in the half-power beam width, which, if you're familiar with optical astronomy, this is the region where roughly half the peak signal is lost. The half-power beam width depends on the pitch angle, the number of turns, the frequency, the circumference of the coil, if it's a helical antenna, and the spacing of the turns. For us, in normal mode, this produces a rather unusual result. When you plug in the numbers into the equations, we pick the turn to maximize spacing. The diameter, we assume the coil was the maximum possible diameter. The frequency here is incorrect, but I don't think it's going to affect the results. It'll actually be emphasizing the results. But when we plugged in the recipe, my students plugged in the recipe for the half-power beam width based on the frequency and diameter and so on, we got the half-power beam width as 3,000 degrees. Now, those of you who know anything about geometry know that you can't have a half-power beam width of 3,000 degrees. It has to be somewhere between 0 and 180 degrees. So essentially what this means, interpreting it, is that we have an all-sky monitor. We have something that's going to be sensitive to the entire sky, receiving signals from the entire sky, and unless the Earth is blocking part of the beam, then we're essentially observing everything that's visible to the satellite. This stands to be corrected. There may be some subtlety that we're missing. None of us are radio astronomers, but the assumption here is that we have an all-sky monitor that's receiving all of the signal from the entire sky, with the exception of the part that the Earth is blocking. Operational modes. If the satellite is tumbling, this means that we have a combination of things happening. If we're just sweeping the sky with the satellite fixed in orientation relative to the stars, then you can figure out what you're pointed at based on the orientation of the spacecraft. If you're able to point at targets, then you can integrate on a target of interest, which isn't going to be possible with STEM-SAT1. So in terms of our situation, it looks like we're going to have a tumbling satellite sensitive to all directions in space. And so we're going to have to look at what we get in accordance to that. So what are the sort of things that we could observe? It's been suggested, again, I've calculated for 300 kilohertz. We can modify that to 20.1 relatively quickly. The cosmic microwave background is a ubiquitous source. My students basically modeled this and got 0.09 Janskys at 300 kilohertz for the microwave background. At 2280 megahertz, Jupiter gives off about 3 Janskys, and the sun at 2800 megahertz gives off 750,000 to 25 million Janskys. In fact, the sun is so bright a source that they have the solar flux unit because the Jansky just doesn't help them. The microwave background. We worked out the flux at 300 kilohertz. We use the fact that the microwave background is a black body source given in the graph at right. It's almost the most perfect black body that's ever been measured at 2.7 degrees above absolute zero. The NRAO, the National Radio Astronomical Observatory, gives a peak wavelength of 2 millimeters and 380 million Janskys per steradian peak power. Well, if we know our frequency and we know the black body law, we can use this to predict what the flux level for any other wavelength or frequency will be. And when we plugged in 300 kilohertz and used the ratio, we got 0.09 Janskys for the microwave background. At 20.1 kilohertz, that number will be even smaller. The further away you get from the peak, the lower and lower the flux levels that you're going to get. I should say flux densities that you're going to get. And as a result, this number 0.09 will be less for 20.1 kilohertz. So we can see that the flux levels for the sun will dominate all other sources. If we have what we now know is a tumbling satellite that's sensitive to all directions, then the only thing that will stop us from observing a source is if the Earth is in the way. Since the sun is hundreds of thousands of times brighter than all the other sources, we essentially have a solar satellite, solar radio astronomy satellite, except for when the Earth is in the way, blocking it. So what sort of solar science can you do? This is a graph of the different parts of the sun. The exterior parts of the sun are the parts that we're most interested in. We're headed towards solar maximum, which is actually a benefit for our satellite. And the sun does a number of things. There are solar flares, which are bursts of energy from the sun. Events happen near active regions. And so we receive radio radiation from all of these. In terms of solar radio, there's 3 basic components to it. The quiet sun, what they call the slowly varying component, and the bursts. Here is a graph of the flux on the vertical axis versus wavelength or frequency, whichever you prefer. Optical astronomers prefer wavelength and radio astronomers prefer frequency. And what we can see here is that the bursts, the hatched area near the top, clearly give more flux than all the other components, which is good for us because that's kind of where a lot of the interesting physics is being done right now. Then there's the slowly varying component and the so-called quiet sun. So what are these things? This is a plot from the Solar Terrestrial Center, and it shows basically the flux at 10.7, and the solar flux units are being used instead of Janskys on the vertical axis. The little orange areas that you see on the bottom are what they call the quiet sun. It's basically the baseline level of radio energy that you get from the sun that it never really goes below. It's basically thermal rate emission. Remember, I just mentioned black bodies. The sun is a black body at a temperature of 5,800 Kelvin on its visible surface. And so there'll be radiation at all wavelengths, including radio. And so when the sun isn't doing anything interesting, we're going to have this lowest level of radiation in terms of radio. And so this is the so-called quiet sun. When the sun is at minimum and not doing much in terms of radio activity, this is the thermal emission from the black body. The slowly varying component is the component that you sort of see here, marking the peaks and troughs that are occurring. This is sometimes called the S component, and it's basically thermal emission, but it's from areas where plasma is collected near active regions and sunspots that give off enhanced amounts of radio emission. So they're associated with the solar cycle. It varies slowly with the solar cycle, and also varies due to the rotation of the sun. If you have an active region, it can appear around the limb of the sun and be visible while the sun is rotating, and then rotate out of our field of view and disappear. And so there's a monthly scale to this related to the fact that the sun's rotation period is about 27, 28 days. And then there's the long waves that we saw on the last slide that are related to the 11-year sunspot cycle. But there are small scale variations in this around roughly a day. And so there is interesting things happening on solar lower timescales. The sort of sexy part are the bursts. Everybody likes explosions and activity and things like this. And there's not time enough here to go into every possible type of burst and what types of things that we would see. This is one of the things that me and my students are still working on, is to try to simulate what a type 1 burst, a type 2, type 3 burst would actually look like at our frequencies. It's normal to plot on these detections the frequency on the vertical axis and then time on the horizontal axis, so that if you picture a cut vertically, it's basically a radio spectrum at that time from the burst. So you're seeing the lowest frequency energy represented as a color, and then going vertically towards other frequencies. So you're sort of stacking up radio spectra side by side versus time to create plots like this. The type 1 bursts are associated with active regions and plasma, and these are very, very short duration. They last a second or two. So in order to observe these things, you need a very high sampling rate. And the interesting thing about these is that they stay roughly the same frequency. You have a radio spectrum that has a peak, and it more or less stays fixed in time. The type 2 bursts are associated with coronal mass ejections, where large parts of the outer atmosphere of the sun can be ejected into space, sometimes almost the entire thing. They develop in the corona, the lower atmosphere of the sun, and then work their way outwards. Now, the interesting thing about this for STEM-SAT1 is that they will start out at a certain peak frequency and then work very rapidly at about 1 megahertz per second drift towards the shorter frequencies or longer wavelengths. Basically, the thing loses energy and the peak frequency shifts towards lower frequencies, lower energy. This is, I think, is where one of the big opportunities for STEM-SAT1 is. Type 3 bursts are associated with solar flares. These are localized, so coronal mass ejections tend to be large scale. Associated with these solar flares and sunspots are basically explosions at local regions. And these drift towards longer energies or lower energies even faster at about 100 megahertz per second. And type 4 and 5 bursts, these are continuum sources associated with solar flares. This is where the fact that the solar flare has a lot of energy associated with it, high temperature, and as a result, it gives off some thermal emission. Now, where the opportunity for STEM-SAT lies is these type 2 and 3 bursts that drift towards longer wavelengths. Essentially, the burst starts in the lower atmosphere of the sun and loses energy as it moves outwards. And the result is that it moves through the outer atmosphere of the sun, the corona, and into the interplanetary region. The issue, however, is that the frequency is drifting towards frequencies that are lower and lower and lower. So if you want to see the entire development of one of these flares from the lower atmosphere of the sun, you really want to see an entire range of frequencies, starting from relatively high frequencies all the way down to low as frequency as possible. But the atmospheric cutoff stops you from doing this. You get to a point where the ground stations simply can't track the radio emission from the burst anymore. And so STEM-SAT1 will be sitting pretty to observe at 20.1 kilohertz that the ground stations can't do. And then that will extend the ability to study these bursts for a longer duration and out into the interplanetary region. And so I think this is the science driver that will make STEM-SAT1 be able to contribute to our understanding of these bursts. I'll point out that Wang et al. In 2021 used the Parker Solar Probe to observe a type 3 burst at 300 kilohertz. Remember, I was focusing on 300 kilohertz. And so this is doable. At least one type 3 burst has been observed at these lower frequencies that can't be observed from the ground. And so I think this is a huge scientific opportunity if we can take advantage of it. As an aside, Jupiter is famously a radio source. The interaction of Io and Jupiter is moderates the radio emission. When the sun is not visible, because STEM-SAT1 for at least part of its orbit will be on the other side on the daylight, from the daylight side of the Earth, then what will happen is that the Earth will block our view of the sun. So for half the orbit, the sun not being visible, washing out every other source, there's an opportunity to observe Jupiter. And so this needs to be developed further. We haven't had a chance to look into this too much, but particularly when Jupiter is at opposition, when it's on the other side of the sky from the sun, then for half the orbit, we'll have a solar satellite, and for half the orbit, Jupiter will be the most strong source. And so there's an opportunity there. We want to maximize the science. And so one of the key elements here is rapid sampling. We saw that some of the bursts occur over a 1-second time frame. And so we're going to want to sample the data as rapidly as possible within constraints, of course, of the hardware and how much data storage and how much we can downlink versus time and that sort of thing. And there needs to be established a data archive with the ability to search by date, target possibly Jupiter or the sun, with proper timestamps, flux calibration, the orientation of the spacecraft. One of the issues with the Jupiter emission is that it's polarized, and observations tracking Jupiter's radio emission over time have had to take into account the fact that the angle of the polarization with the antennas can moderate the flux that you're getting. When we've measured the half-power beam of STEM-SAT1, we'll know more about that, whether that's going to be an issue or not. We also want to start reaching out to people that are actual radio astronomers. I've reached out to an astronomer at Marshall Space Flight Center that has some experience with radio solar observations. There are other projects that are observing Jupiter and so on. And so we need to start going to some of the scientific meetings and reaching out to people and developing some proper science teams to take advantage of the data. And also just from a professional aspect, you know, the people that are working on constructing and building the spacecraft and testing it out, we need to sort of develop a little bit of a policy for how those folks will be recognized on any publications that come from the data. So that'll be something to be addressed. This screams out for citizen science. And one of the things that I find interesting are these bursts. Somebody is going to have to identify bursts when they happen in the data. So you'll have a flux calibrated timeline of observations from the satellite, and somebody's going to need to pick through the data. The way the Kepler project did it, looking for transits of planets, is that they simply dumped their light curves onto the web, and people were allowed to get a graph of the data and look for transits of planets. The bursts are basically the inverse of a transit. Instead of a dip in brightness, you have a increase in brightness, but the principle is the same. So I could easily see a project being developed where someone goes to our website, downloads the data, and then identifies bursts and what type they might be based on their appearance, and then uploads the results, and we create a database from the different citizen scientists, the way Kepler did for possible bursts. And this could be of great use to the scientists. And of course, Radio Jove is an active project, and there's a group using the Gavert telescope that's monitoring the sun using citizen science and students. And it's an obvious collaboration to collaborate with them, coordinating their frequency observations with ours. And I'm open to any questions. I covered a lot there very quickly.
Bruce said 1 SFU is equal to 10,000 Janskys. Kent Gardner, some spacecraft have recorded whistlers from Jupiter. Will this CubeSat be able to do the same as around 5 to 15 kilohertz as we do on Earth?
Maybe. I really haven't had a chance to look into the Jupiter stuff because we got into the weeds with the solar project. My feeling is that if the sun is not in the sky, the Earth isn't acting as a barrier for the solar, then Jupiter is our target. Because if you look at the cosmic microwave background, it's hundreds of times fainter than Jupiter is. And the galactic sources are going to be even weaker. Those are sort of millijansky type things. So we're looking at, Jupiter when the sun is not in the sky. But Jupiter gives us synchrotron emission. And so we need to know what the synchrotron exponent alpha is to calculate what the fluxes are from Jupiter. So this is once we've done some estimates of fluxes from the sun, Jupiter is our next project. But the difficulty is that you can't be an expert on all of these things. So I'm still learning radio astronomy and synchrotron emission and things. But yeah, definitely Jupiter is of interest. And I don't have any reason to believe that the satellite wouldn't be able to pick up Jupiter emission.
You might have your students look at our YouTube channel, SARA YouTube channel. We've got the entire Radio Jupiter team, what I bet would love to collaborate on this one. We got all their YouTube videos. Let's see, Ed Harfman, being an optimist for once, radio astronomers' history is replete with people looking for something else and finding the radio universe. Okay, Ed is our resident philosopher and computer scientist. So, okay, anybody else? What is the effective sample rate of VLF receiver from Bruce?
That might be a question for Wayne. That's a hardware question. My feeling, though, scientifically, we have these short type 1 bursts that last, a second or two. So my feeling is that we want to make the sampling rate as fast as we can. But of course, the satellite can only store so much data. And, there's limitations, with the boards and the electronics. but my feeling is that we want to sample as fast as possible.
My experience of sizing that stuff is, how much you have storage and how often you're going to be able to downlink the data, and the combination of that will provide you your sampling, how much samples you could take in between downloads.
That's exactly correct. Yeah, and until the hardware is finalized, it'll be hard to know what that answer will be.
Right.
And a lot of people are working. A lot of people are working really hard on that.
Yeah, so we can provide some answers to that in the not too distant future, because we're creeping up on having that receiver characterized pretty much.
And once we have the receiver characterized, we'll have more solid information about Jupiter and so on, because the antenna will be sensitive to a certain level, and that'll determine what sources we'll be able to take advantage of.
So a question on potential terrestrial RFI. I guess the scenario would be when you're trying to detect signals from Jupiter when the Earth is blocking the sun. I'm wondering if there's any terrestrial VLF, such as what comes from the submarine transmitters. Will they penetrate the atmosphere going up and cause RFI?
I'm not familiar with what frequencies they use, so
they're right at the same frequency.
20.1 kilohertz is a great frequency for those guys.
That's what the super SID antennas use.
Right.
Depends
Well,
on the bandwidth of the receiver, right? And whether,
well, my understanding though is that these frequencies are reflected by the ionosphere, and so they would presumably be reflected back down towards the Earth by the ionosphere.
Yeah, that's what I don't know.
Yeah, I think.
However, as far as the Earth, one of my Earth science friends who likes to make my life difficult commented that when there's solar storms, then we'll have charged particles hitting the Earth's magnetic field, and that could potentially create very low energy radio emissions. And he thought that, we should maybe look at that as a possible geophysical source. And that was last week. So I have not had any chance other than despair. I was like, okay, if the Earth is a source, then, we really need to work at it. But typically synchrotron emission, the electrons had to be moving fairly rapidly in order for them to produce any significant energy. But it's another fly in the ointment that we need to look at. We at least need to look at it enough to dismiss it.
Yeah, I think that you could probably find the exact transmitter that does anywhere near close to 20.1 kilohertz in the list, the super SID list. And then we can maybe determine when to filter that out, depending on where it is in orbit or something.
But it should be reflected by the ionosphere. That's the whole point, is that these wavelengths are reflected.
A lot of it's reflected, not all of it. We get the ionosphere reflects part of it, but a bunch of it goes to space, and it changes. So there's a chance that where the ionosphere is, it may not reflect at all, and you may get signal coming up to the spacecraft. Bob, you had a question?
Yeah, I want to make some comments. First of all, I think you're doing a great job here, and your talk is very good. And I think you're probably in a position where you're learning a lot, and your students are as well. And there's just a tremendous amount to be learned. There's another group called HAMSI that was having a conference this weekend that I was trying to keep up with also, that I participate with. And there's a fella by the name of Bill Engel that's at the University of Alabama, so up the road from me, I guess, that you probably ought to go try to meet and just visit with him a little bit and understand what they're doing. But they're setting up a data collection of information that's going to come from hams and other people running a science station on Earth that's going to collect a variety of VLF data and magnetar or magnetic field data, and really looking at the effects of the sun. Okay. And then also we have, as Rich mentioned, several people here that know a lot about the sun that have talked about it in great depth. And there's also a large group at the British Astronomical Society that has a lot of good video, some of which are video or optical observation things, but they also have an active effort to monitor the sun. So there is a lot of information out there available to you.
Yeah. Yeah, I'm an optical astronomer. We always say that PhDs are an inch wide and a mile deep. So it takes years to become an expert on any one of these things. You know, Jupiter, the sun, cosmic microwave background. People spend years, you know, developing their skill set. And so I'm kind of jumping in the middle. And so we really do need, you know, to broaden the scientific group with people that have expertise in different things, because no one person can become an expert on research on all of these different areas. You know, and the more you get into it, the more complicated it gets, as always.
Well, just the fact that you recognize that is good, because most of us don't. We try to do it all.
Well, you know, I told my student that's working with me this semester, David, that I said, look, I'm not a radio astronomer, so we're going to be learning this together. And there's going to be times when you're going to ask me for help, and I'm not going to know the answer because I'm going to need to figure it out. You know, radio astronomers train for years, and I don't have years to get myself up to speed. And, you know, I joke that, you know, the science team for STEM-SAT1 is me and 2 undergraduate students, and we need to make that science team bigger. You know, so I'm definitely trying to reach out to people and bring in more expertise and more experience.
Yeah, and I might reinforce what Mel is saying. This is Wayne. Definitely Mel is the lightning rod for the science group. He's handling that portion of it, whereas a lot of us are doing the logistics and the hardware side of things. So the science experiment, while it is the second priority in the whole project, Mel is it, and he and his graduate students are it. So we would welcome
undergraduate students.
Undergraduate, yeah. So we would welcome participation by any and all who have an interest and some time to spare. Really, and would really appreciate that.
I'll make one more comment. You know, I've been involved in AMSAT since in the 80s and built hardware that's on satellites myself over the years. And I'm actually working with a group of people here at AMSAT on the PACSAT board. It'll be a transmitter and receiver, and we have to make all kinds of decisions about how much data we have available and how fast it can be transmitted, those kinds of things like you were talking about. And the other major thing is the current consumption on the satellite. But I think you might get to a point where you could come up with some way to process some of the data and not be trying to transmit all the information back, but figure out what you want to learn or what you want, what's important from the data, and process it in space on the satellite, and then just transmit some of the results back. And that would save you some transmission time if you get to the point that you're constrained by the downlink.
Yeah, that's a good idea, except for the philosophical comment that was made. If we predetermine, you know, sort of how we're going to process the data and then downlink it, then we could lose opportunities, because as Wayne has also pointed out, no one's done a lot at these wavelengths, right? This is a relatively unexplored band of the EM spectrum for astrophysics. And so downloading all the data is preferable because we don't know what we could find. And if we, you know, follow, and your suggestion is a good one, if we're limited in what we can download. But, you know, no one expected the fast bursts, right? These little spikes of radiation coming out of the blue, and there they are, right? You know, you know, so a discovery like that might be missed if we do too much processing. But anyway, that's just a general comment. Things are very much a work in progress.
All right. Any other questions for Mel? All right.
Comment there that yeah, I kind of wonder with the magnetic antennas, well, any kind of antenna is you'll basically have a directivity to it, a direction that it receives, a direction it doesn't. With the satellite tumbling, it almost seems like it'd be nice to have the three of the magnetic rods all at right angles to each other, kind of like the isotropic probes you see in a test lab if you're doing any antenna testing or anything. Unfortunately, that's a lot of complication because that'd be three, you know, pickup coils, three receivers, and then sum the power of the three for a power. But seems like that would have a certain desirability with a tumbling satellite, but it also sounds like it may not be anywhere near reasonable to put together.
Well, my understanding is that it's going to be a helical antenna. And so that will be a single sort of looped antenna that I showed sort of like in the cell phone. I'm not familiar with the toroidal antenna, but that's a possibility. But the helical antennas, this thing tumbling, basically it's going to be observing all the flux coming in from all the angles. And the helical antennas have the advantage that they can receive circular polarization. And so that will eliminate some of the need for having multiple dipoles or whatever. I hope I explained that right.